So let us recap quickly what we were doing. We were trying to find the Durham cohomology ring of the torus. To that end, first we want to study the vector space structure of this cohomology ring. Right, so we started with finding a real vector space basis for this cohomology ring. We defined the one form alpha and beta on the torus to be such that their pullbacks are the form dx and dy on R2. Then we claim that an R basis for the cohomology ring is going to be 1, alpha, beta, and the wedge product of alpha and beta. And from this, we immediately see the algebra structure. We see that as a real algebra, the cohomology ring of the torus is just going to be the exterior algebra on two generators. So generated by alpha and beta, and subject to the relation, the alpha square is 0, beta square 0, and alpha beta is equal to minus beta alpha, which are properties of the wedge product. Alright, so now we want to complete the proof that these form a basis, a real vector space basis for the cohomology ring. Previously, we have shown that 1 form a basis for cohomology in dimension 0, and alpha wedge beta form a basis for cohomology in dimension 2. Recall that we proved this by evaluating this integral. So this integral is not 0, and thus alpha wedge beta is not exact, i.e. it's not a 0 element in the cohomology group. So then it must generate this whole cohomology as a vector space. So now it remains to show that the cohomology in degree 1 is generated by alpha and beta. So the idea of the proof is as follows. We'll define the following two curves on R2, right, C1 and C2. So these correspond to these two loops on the torus. Now we claim that it suffices to show that the integral, right, of alpha and beta along C1 and C2 are as follows. So why would that be sufficient? Well, first of all, because integral of alpha along C1 is not 0, and because integral of beta along C2 is not 0, we know that alpha and beta are not 0 in the cohomology group. Moreover, alpha and beta must be linearly independent, because if alpha is a multiple of beta, or vice versa, then this integral here of alpha over C1 must be a multiple of the integral of beta, right, over C1. And so 1 must be a multiple of 0, which is a contradiction. So alpha and beta are non-zero and they are linearly independent, so they must generate this H1 as a real vector space. They must form a basis for this. Thus, it suffices to compute the values of this integral, and that's what we're going to do now. So let C1 be the curve t maps to t, 0, and C2 be the curve t maps to 0, t. Then observe that the integral of alpha and beta over C1 is just equal to the integral over the interval 0, 1, right, of their pullback under this map. This in turn is just integral from 0 to 1 of the pullback under C1 of dx and dy. Because recall that by definition, alpha and beta pull back to dx and dy under the projection pi. So now what are the pullbacks of dx and dy under C1? What are these one form here? Now this pullback of dx is just going to be d of the pullback of x, right? Now the pullback of x is just going to be the x coordinate of C1. So this is just t, and then here this is just the y coordinate of C1, right? And so that is just 0. So this is just integral from 0 to 1 of dt, so it's 1. And this is integral from 0 to 1 of 0, so this is 0. Thus indeed we have shown that integral of alpha along C1 is 1, and integral of beta along C1 is 0 as claimed. Now it's not hard to show, it's exactly the same to show that integral of alpha along C2 is 0, and integral of beta along C2 is going to be 1. Thus, from our discussion before, we see that alpha and beta must be linearly independent, and they are also non-zero in the cohomology. Thus, they must generate the cohomology in degree 1 of the torus. Thus, we have proven that a real vector space basis of the cohomology ring of the torus is given by 1, alpha, beta, and alpha wedge beta. And then we see that alpha and beta must generate this cohomology ring as an algebra. So then this cohomology ring is just an exterior algebra on two generators, alpha and beta of degree 1.